Hello, calculus fans! Okay, so we're going to move on to an entirely new topic now, where we're going to talk about applications of derivatives. We've spent a long time working on our ability to compute the derivatives of many different kinds of functions, and now we're going to work on something different where we apply that knowledge to be able to solve real problems. So one of the most important applications of differential calculus, which is what we're studying, are optimization problems. We're going to look for the optimal or best way of doing something. Let me give you a few examples of the type of problems that we're actually going to solve in this class. You have a manufacturing plant that is creating cylindrical aluminum cans, like soda cans. And the question we want to ask is, what is the shape that will minimize manufacturing costs? You have a certain amount of volume that you can fit into a can. What's the best way of designing a can? Do you want to make them short and flat like tuna cans, or long and thin like Red Bull cans, or something in the middle like soda cans? And depending on your constraints, you might have different answers. You have a dog that's chasing a ball from the beach into a water, and they're not running directly towards the water. They're sort of taking an angle. Maybe the line between the person throwing the ball and where the ball lands is not a right angle with the shoreline. So the dog can obviously run faster on the beach than it can swim. What route should the dog take? Turns out dogs instinctively solve this problem pretty well in practice. We'll be able to use calculus to solve this problem exactly once we know a few parameters like how fast does the dog run, and how fast does the dog swim, and what's the geometry of the setup. A farmer wants to fence off a rectangular field alongside a river. So this means that the farmer does not need fencing along the fourth side. They use the river as sort of a natural fourth fence. But the farmer only has a fixed amount of fencing available. Maybe they have a particular budget in mind for how much they're going to spend. The question is, what dimensions should she build the fence in order to maximize the area of the field that is going to be fenced off? What is the longest pipe that you can carry around the corner of a hallway? So you have this long, rigid pipe. You can't bend it. You can't disassemble it in any way. If you're going to hook that pipe around a corner, you want to know what's the longest pipe that actually can make it. So if the hallway is kind of narrow, then maybe there's sort of a fixed length that can actually make it around the corner. Now, the way we're going to solve these problems is we're going to find the maximum or minimum values of a function. So let's make a definition now about these maximum and minimum values. Now, we've talked previously about local maximum and local minimum values. We're going to do something a little different now. So we're going to say that the highest point on a graph is the absolute maximum, and the lowest point is the absolute minimum. Well, let's make a precise definition and then take a look at a picture. So the definition we'll make is for absolute extrema. We'll let c be a number in the domain of a function. Then we'll say that f of c is the absolute maximum value of f on its domain if f of c is bigger than f of x for all x in D. And the other way around, it's the absolute minimum value if f of c is less than or equal to f of x for all x in D. Just a bit of notation, this thing that looks like kind of the head of a pitchfork, that's mathematical shorthand for is an element of. So right here, when we write x and then that little pitchfork symbol, x is an element of D, or sometimes we'll say x is in D. And then just to clarify the language, the word extrema, this is a catch-all word that means both maxima and minima. And then the words extrema, maxima, and minima are plurals for extremum, maximum, and minimum. So if you say extremum, that means it's either a maximum or a minimum. So I wanted to take a look at a graph just so we can see the idea of working with absolute extrema and local extrema. We've talked about local extrema before, but now let's identify absolute extrema on this graph. So in this picture, it's pretty easy to see that this is the lowest point on the graph, the point P. So what we'll do is we'll say that there is an absolute minimum at x equals a. That's where the absolute minimum is. And then f of a, whatever the y value is, that is the absolute minimum. In a similar way, this point U is the highest point on a graph, so that we're going to say there's an absolute maximum at x equals e. That's down here. And then we'll also say that f of e is the absolute maximum. So we have to say where the maximum is and then what the maximum is. What the maximum is the y value at that point. Now, in addition to the absolute extrema, those are the highest and lowest points on the graph, we can also talk about local extrema. That's the highest point or maybe the lowest point in just a small area of the graph. And we've talked a little bit about that before. Let's make a precise definition. So we'll say that the number f of c is a local maximum value if f of c is bigger than f of x, just when x is near c. So it doesn't have to be throughout the entire domain, just near. And then the same thing for a local minimum value if f of c is less than or equal to f of x when x is near c. So you just have to be close by. And now to be precise, the phrase near c means on an interval containing c. Okay, so I've scrolled past the picture. You can't see it anymore, but hopefully you can go back and take a look. There's local minima at x equals b and x equals d. That tells you that locally, near b and near d, those are the lowest points that you see. And then there's local maxima at x equals 0, x equals c, and x equals e. So near those points, they aren't necessarily the highest point of the entire graph, but they are the highest point near those values. Now, I'm also not going to say that x equals a is a local minimum, and I'm not going to say that x equals g is a local minimum. Part of the definition requires us that endpoints cannot be local extrema. Okay, that's all for now.